I'll be presenting topology optimization in plasticity and quasi-brittle fracture using a Levet-set method on FreeFEM. I'm doing a PhD. It's funded by ERT System X. My supervisors are Gregor Allaire from École Polytechnique and François Jouve from Université de Paris. So the content. First, I'll be presenting the quasi-brittle fracture model, its implementation on FreeFEM, followed by plasticity, its implementation, the shape optimization. I'll be going very fast with shape optimization, and then I'll finally present a few numerical results for the two physics. So the context. So damage, which is degradation in material, and fracture often occurs very often in concrete structures, very often in bridges, in buildings, etc. And so does plasticity in metallic parts. And which is to say that like you have these phenomena and you need to optimize structures for damage, fracture, or plasticity. But most research in structure and shape and topology optimization is on linear elasticity, be it density or level set based. And very few works focus on structure, on fracture and plasticity. And more so, like even if they do, they just consider the discretized, the time and space discretized version of the plasticity and fracture problem for sensitivity analysis. So now I'll be introducing the quasi-brittle fracture model. Let's say that you have a solid on the left that is fixed at the bottom, forced on the top with a force G. And let us just assume that the force G assumes a very high value. So in that case, the solid omega can undergo something called as a brittle fracture, which is to say that the stiffness does not change anywhere in the material once the crack has formed. And then this is governed by the 3 laws of crack evolution given by Griffith 100 years back. Then it might also, the structure omega might also undergo something called as a quasi-brittle fracture, which is to say that there will be a crack formation, and around this crack, there will be damage, which is to say that degradation in the material property or the stiffness, as you see in the figure on the left. And this is modeled typically using damage gradient energy. And there is another model which is called as a phase field model, but I'll not go into the details. And then the structure might also undergo something called as ductile fracture, which is to say that there will be first plastic deformation, and then there will be damage followed by the crack formation. And this you can model using a damage gradient energy plus plasticity. And yeah, I'll be talking about quasi-brittle fracture. So I'll quickly introduce linear elasticity. Let's say you have omega, which is a shape, which is a solid, and 0 to t be the time interval of interest, u be the displacement vector field, C0 be the Hooke's tensor, epsilon be the strain tensor, and then let's say that G of t is a time evolving force. Then I would consider the quasi-static evolution law, which is the following. And I assume every one of you must be familiar with it. Now I'll introduce the fracture energy. Let's say that as you saw before, that the stiffness changes. So you need to parameterize the stiffness using some parameter, and I'll use alpha, which takes value between 0 to 1. And it is typically called as a damage parameter. And the Hooke's tensor C will now be a function of alpha, so we'll call it C of alpha, such that at alpha equals to 0, it takes a value say 0, which is to say that there's no damage. At alpha equals to 1, say of 1 is equals to 0, which means that there is a crack, like the stiffness is 0. And as and when alpha increases, the stiffness must go down. Let GC be the fracture toughness. Then the elastic energy shall be given by capital E, which is if you take alpha equals to 0, you'd see that it's a typical elastic energy. And in this case, we've just replaced C by C of alpha. Then the fracture the total mechanical energy shall be given by capital E plus a constant GC times the crack length. And this is typically known as Frankfurt-Marigot energy. And when you minimize this energy with respect to the displacement u and a crack boundary gamma c, then you can determine the crack for a brittle fracture, and you can also recover the 3 laws of Griffith. And in order to use this to model quasi-brittle fracture, we simply take the second term, which is GC times the perimeter of the crack, and we regularize the perimeter using Ambrosio-Tortorelli regularization, which is the same regularization as Benjamin presented. And so here we have to introduce a few new constants. There is CW, which is an empirical constant. There is L, which is the characteristic length. and there's W alpha, which is the fracture energy density. And you can show that using gamma convergence, that as L tends to 0, WL, the minimizer to WL converges to the minimizer of W. So now the total energy should be the mechanical energy minus the work done by the force. And I quickly introduce the set of damage variable D, which is to say that alpha is at least H1 and it takes values between 0 and 1. The set of test variable D, which is just we need a space for test directions, which is just functions which are positive, and H1. The space of displacement, which is H1 0, which is obvious. And the quasi-brittle fracture model is saying that I want to minimize PL in 1 along directions in H10 times DE such that the irreversibility condition is satisfied. What is the irreversibility condition? It is saying that alpha dot is positive, which is to say that damage or alpha can only increase, it cannot be reversed. So then this minimization 2 for beta for the test direction alpha dot is given by the following, which is just so if you put alpha equals to 0, you'd get the linear elasticity variation formulation. And for v equals to u dot, you get the following inequation, which is also known as damage criterion. And yeah, so now we have to, for the fracture problem, we have to solve 3 and 4. You see that it's in terms of u and alpha, and it's non-linear, it's coupled, and it's an inequation. And there is no unique solution. This problem is posed, and the existence for the dynamic version of the above was shown by Christopher Larsen a few years back. And now, in order to implement this on FreeFEM and to study it theoretically for shape optimization, I approximate 3 and 4 using penalization. So now, which is to say that I had a constraint on alpha before, alpha was between 0 and 1. Now I let it take values in R, which is to say that I remove the constraints. And the equation 3 remains the same as before, whereas the equation 4 becomes 6. And in 6, you see that the equation, there's just one term in red, which I have added, and the inequality sign is replaced by an equal. And this term, as you see, which is a penalization term, is so constructed such that as like epsilon, the penalization constant over there is taken to be very small and positive. Alpha would try to be in the neighborhood of epsilon. Sorry, like if alpha violates the constraint that of crossing 1 or alpha dot being positive, it can only do so in the neighborhood of epsilon. And now I'll quickly talk about the numerical implementation of 5 and 6. So I'll do it using finite element method, unstructured mesh, and the maximum mesh size must be less than L. I take epsilon equals to h max square. This is for theoretical reasons, and I divide time interval 0 to t in n intervals, index 10, and then we can solve 5 and 6 using an implicit scheme. And this was given by Kim Pham, Jean-Jacques Marigot, and his team. And which is to say that we solve for un plus 1 and alpha n plus 1 all in implicit. And in order to solve it, we cannot apply a Newton completely, which is to say that if you were to couple u alpha and you were to solve, you try to find the second derivative and apply Newton, it's not going to work. It would diverge. But rather, what works, as they showed, was a fixed point Newton, which is to say that you solve 7 for un plus 1, and then you solve 8 for alpha n plus 1, and then you iterate, and then you go back to 7, and then you iterate until convergence. And this works perfectly fine, except it's a bit slow. I'll first show, I'll just show a small snippet of the code, and then I'll show a numerical result. Okay, so on FreeFEM has this wonderful feature of macros, which is like if you have a very big tensor, or if you have very complicated functions, you can just throw all of them into macros. And as you see, like I create a macro for everything. I define constants, then I define the Hooke's tensor, I define a macro for residual, and then a small problem for Newton in alpha, and then so this is the main part of the code. I just introduce the functions, the P1 functions, and then in the loop you see I just apply that fixed point Newton algorithm wherein I update alpha p, and then I solve the linear elasticity problem, and then I solve the new for the Newton, and then I iterate until the difference in alpha minus alpha previous is less than some tolerance. So now a 3D example. Let's say I take a column which is which is which is fixed at the bottom, forced on the top, and I take concrete properties, which is to say that I take C of alpha as S1 minus alpha square, and W of alpha as linear, and this geometry has around 102,000 DOF. It's P1 for U1 alpha. The time interval is taken to be 0 to 1, and there are 8 time steps. Here is the mesh, and here is alpha at t equals to 0. It's gray or it's white, which means that there is no damage at t equals to 0. And as and when the force increases, there is there is damage, which is to see that which is you see that there is alpha, like there is a small band where alpha equals to 1, and that is exactly where the crack has formed. And and this simulation took around 5 hours, and I haven't put this code in parallel. I haven't applied any preconditioner because, like, okay, finding a preconditioner for a nonlinear problem is not that evident, and yeah, it might take me some more time to do that. But yeah, anyway, I'll talk about the optimization part later on for this, and then you'd see that applying an shape optimization for several shapes, it's very costly. So plasticity, I'll be a bit quick. There'll be a small crash course. So let's take a bar, a metallic bar, and we subject it to uniaxial loading, which is to say that you just stretch it from both sides. Then you know that it deforms in elastic manner until the time the stress reaches a limit called sigma zero, which is just the elastic limit. And then after that, once that stress is reached, all deformations, like the deformations after that stress limit are all plastic, which is to say that they are permanent. So which is to say that you see in the diagram, epsilon p is the plastic deformation and epsilon el is the elastic deformation. Now, if you were to subject the same solid in triaxial loading, which is to say that you just stretch it in three directions, then you would find that for the principal stresses sigma 1, sigma 2, sigma 3, uh, in the following graph, there is an elastic domain which becomes a closed convex uh, surface given by the iso zero of f of sigma. F of sigma is just a function which is the yielding criteria, and that could be one misses, that could be Tresca, that could be, like, there are many criterias. And you say that where f of sigma equals to 0, I have the elastic limit, and when f of sigma is less than 0, there's the elastic domain, okay, which is to say that all deformations or all stresses inside of f of the inside of the domain, which is in k, are all elastic, and on the surface they are plastic. Then if by chance this happens in solids, if the stress limit evolves in time for some reasons, it might just evolve, it happens, then we call this phenomena as hardening. And this stress limit just could either could either shift, which is to say that the center moves by a value, let's say q. If that happens, we call it kinematic hardening. And if the surface expands, it inflates, then we call it isotropic hardening. So then, using like for the two kinematic and isotropic hardening, we have the general form of the elastic surface, which is f of sigma minus q, which is to say that sigma has been replaced by value q, and I've added minus g, which means that we have added the isotropic hardening, which is the how much the limit has inflated. So now a few definitions. So we have omega, which is the domain. U is the deformation vector. Epsilon u and sigma, they're the strain tensor and the stress tensor. Epsilon p and q, they are the plastic strain and the hardening stress. Gamma and g, it's like there is an internal isotropic variable. I'm not getting into that. And there's a corresponding force g, which is what you just saw. C is the Hooke's tensor. H is the hardening tensor. Epsilon is just E, so is just the isotropic hardening constant, which is to just say that how difficult is it to move to inflate the limit. B and G be the body surfaces and body and surface forces respectively. So rho T be the time of interval of interest. Sigma Y be the yield strength. Then here are the governing equations. So yeah, there are a lot of them. The first one is something that all of us know. The second equation is just the constitutive equation. The third equation is the one misses yielding criteria. The fourth one is the kinematic hardening law. The fifth one is the isotropic hardening law, and then the rest I'll probably not go into the details. It might take a lot of time. So in order to solve these equations, what we typically do is we impose something called as the consistency condition, which is to say that we we say that we just look at the equation, the system of equations 9. We say that f dot should be equal to 0 for mathematical reasons. And when you do that, you end up with the following relation, which is sigma dot equals to some matrix D times epsilon dot U, where D is given by this, which is also known as the tangent matrix. And you see that tangent matrix is 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 easier to write on paper, but it's horrible to code because you have a tensorial product and then you have a contraction, and yeah, like you need extreme precision while calculating this. So the system of equations 9 that you just saw is typically resolved using implicit Euler scheme, which is what is coded in every commercial software. And and in this scheme, like you see that there's several equations, and the algorithm is very simple. It is just to say that we'll start off with delta epsilon, some test. It is just a guess epsilon. For this guess epsilon, we'll find zeta, and we'll find epsilon un plus one, which is the final relation using the tangent matrix. And then we'll see if it was the same as before, or how different was it, and then we'll iterate until convergence. And this can be done easily using the macros of FreeFEM. And this time I'll not show the code because it's just too big. And yeah, like for this case, given that I'm dealing with tensors, I need and these are tensorial functions, I need to write the equation for every element of the tensor. So now I'll show a numerical example directly. So I take Miles-Lee properties. I'll not go into why how we determine E is one and H, and then I take P1 elements for U and P0 for epsilon P and gamma T, and the time interval is taken as 0 to 1. There are 10 time steps, and so there were 140 degrees of freedom, and this simulation took about 1 hour. So this is a mesh, and the support was fixed at the bottom on the four legs, and it was forced at the top along the vertical. So yes, this is the one misses stress, which is just the modulus of the deviatoric of the stress. And this is the plastic deformation. This is the zone that underwent that undergone a plastic deformation. Now, now I'll quickly talk about the adjoint method, which is to so now I'm the framework of shape optimization, and I'll do that using the adjoint method. And let's say you want to find a shape omega such that the following functional j of omega is minimized, and j of omega depends on, as you see, u and alpha, which themselves depend on omega. So yeah, I'll be talking about the adjoint method only for fracture. For plasticity, I'll just leave it. So we can compute the shape derivative using Sia's technique. There are other techniques, but we consider Sia's technique over here with a Lagrangian L, which is a function of the shape, u and alpha, and v and beta, which are the adjoint variables. You can also see them as Lagrange multipliers. And the idea is just to say that I want to minimize j of omega, but j of omega has u and alpha which are dependent on omega, and it's very complicated to differentiate u and alpha with respect to omega. So instead, I'll just assume that u and alpha, they're independent of omega, and v and beta are also independent of omega, and I'll simply optimize the Lagrangian 10. So Lagrangian 10 is just the objective plus equation 5 and equation 6 taken as constraints. So for instance, in case of fracture, it's the Lagrangian should be given by 11, and in case of plasticity, I'll just make a small remark. It would be the penalized primal formulation of the equation of the system 9, and this we present in an article we'll be publishing next year. It's very technical. So the optimality condition on the previous Lagrangian with respect to v and beta shall give us the equations 5 and 6. The optimality condition with respect to u and alpha shall give us the adjoint equation with this shall give us the adjoint equation to determine v and beta, and these adjoint equations are by default linear. And yeah, when you differentiate L with respect to omega, this is easier because we've assumed u and alpha to be independent of omega. So once we differentiate it, we get the shape derivative. And yeah, the adjoint equation that we find in V and beta is not positive definitive, which is to say that it might have zero eigen. If you construct a matrix, you might just end up with zero eigenvalues. But we show in an article we'll be publishing next year, which is that it is still it is nevertheless well posed under certain hypothesis. So now I'll quickly talk about the level set method. Let us just say that you have a shape omega and you want to capture it. Uh, and Yeah, so question is why? Because in the previous slide I showed that I have a shape derivative. Once I have the shape derivative, I need to move my shape along the shape derivative. Of course, I can take the shape derivative directly and just move all of the vertices of the mesh along the shape derivative. But this does not help me to capture the changes in topology. So I need a different way. And one very well known method is the level set method, which is to say that given a domain omega, I'll define a level set function phi, which is defined in the entire space Rd, such that it is positive outside the domain, negative inside the domain, and zero on the boundary. And then we shall move the level set function using by solving the Hamilton-Jacobi equation with the velocity v, which is the shape derivative of j. And yesterday, Howley he presented a different advection using reaction diffusion equation. Uh, and yeah, so here I would be optimizing the shape using the level set method, which is this following level set method, because they're very there are a lot of level set methods, and one might get confused which level set method one is using. So yeah, and this shall be coupled to body fitted tree meshing. I'll show what is body fitted tree meshing in the next slide. So let's say that you have a shape which is given by the Statue of Liberty on the left, and I have the level set of the Statue of Liberty. Don't ask how. And given this level set, I can capture the shape using the body fitted mesh as you see on the right. And yeah, once I have this shape, I can compute the solution on this shape and then find the shape derivative, solve the Hamilton-Jacobi equation, and iterate. So now the algorithm is probably clear, and I'll move to numerical results. First, for quasi-brittle fracture, let's say I want to maximize the total energy, and I consider concrete. I take up a cantilever, as you see, with the following dimensions, and it's forced on the right with a vertical force. And here is the optimization video. So you would be seeing a cantilever, and you would be seeing the plot of alpha. Wherever alpha is red, there's a crack, and wherever it's blue, there's no crack. And you see that.
So, Jed, no more than 3 minutes.
Okay, sure. Sorry, I'll be fast. So yeah, so we've obtained the form on the right, and if you were to do the same simulation for linear elasticity, we obtain the form on the left, which is topologically the same, but it's a different form. And then I optimize a column in 3D, and yeah, so this column so the one you see was optimized for linear elasticity, and I took up the same column and I optimize it for fracture, and you'd be seeing cracks appearing in black almost everywhere in the structure. So I obtained the column on the right, and the one is on the left is for linear elasticity. And yeah, if you were to subject the form on to the fracture model, you'd get a crack. So which is to say that our form is crack free. And yeah, so now I'll move to plasticity. And I'll I'll minimize total compliance, and I take up mild steel. And yeah, so you see that for this cantilever, this is the initialization. This is the plot of one misses stress, and I obtain the same topology but a different form, and which has lesser plastic deformation. And another example in 3D where it's a full-legged support as before. This is initialization, and this is the final shape. And yeah, so conclusion. So level set based topology optimization works for quasi brittle and fracture. And for plasticity, the shapes are very close to the ones obtained for linear elasticity. The perspectives are I can probably use the inverse of linear elasticity operator as precondition for plasticity. And yeah, I can also think about implementing the two solvers in parallel and coupling the two to optimize for ductile fracture. So here are the references, and thank you for your attention, and let me know if you have any questions.
So thanks for these talks, and you have just time for one short question, if you have.
Yes, hello, Jeet. I have a small question.
Yes.
In the plasticity case, for example, if you use the radial return algorithm, do
Yeah.
you obtain a non-symmetric matrix for the tangent matrix?
No.
Is
Okay. So yeah, it depends on the material properties, but the one that I obtain is not is symmetric, dissymmetric.
okay. Thank you.